Evening. This is week 6 of Mechanical Engineering course 5710, Collaborative Engineering. And this week we're going to talk about the connection between Six Sigma, or what we know as process capability, CP and CPK, versus the control charts. So we have this triumvirate. We have these three things working together. We have process capability on one side, which talks about, and Six Sigma is part of process capability. It talks about CP, CPK, and reject rates. And that's a population view of the world. And then we have control charts, which is a sample-based system to monitor the quality and the progress of quality in the manufacturing floor. And then we have the defect rates, or the CP side, that determines the connection between the two. So we have these three things. And this week, we're trying to tie the two together. And that's what the homework for week 6 tries to do. It tries to tie in the three pieces: reject rate, to process capability, to control charts, or control charts to process capability to Six Sigma or CP/CPK. So these are the three things that we're going to try to check together using different components of the system. So I thought before we start week 6, we'd take a high-level review of the concepts that we talked about, because I think students too many times get too involved in the nitty-gritty of taking the data and then applying the formulas and getting an answer without thinking what these concepts trying to do. So I thought I'd take a few minutes before we start to try to connect these three things together for you from a high level, from a systems level. And then we can talk about the details in terms of the numbers and the different systems that we implement quality, whether in manufacturing as control charts, and whether in design as Six Sigma or CP/CPK. So I thought we would do a little bit of a review first, then we go over chapter 6 slides. Then the second half, as we are approaching week 7, which is the midterm, is I would do a short review of the midterm. We're not going to have a video pre-recorded chat or a live chat on week 7, that being the midterm. Normally in a graduate course, we give the midterm, and there is no lecture during that time. So this would be the opportunity to do a review and kind of prep you up in terms of presenting for the midterm. The midterm is going to be pretty much like an assignment. It will be released on a Sunday evening, and then it's due the following Sunday. So you have a week to do the midterm. It's not timed. There are 10 different questions in the midterm, and you are supposed to, or please, only answer the question number that correspond to your UMLID. There are 8 questions in the midterm, and each question is worth 3 points for the first 7 questions, and the last question is worth 4 points, to add up for a total of 25%. So this is the last chance, last lecture we'll have before the midterm, and then we'll meet after this in 2 weeks to begin to talk about the second half of the course. The second half of the course will start with using Minitab to try to do all the quality and process capability and control charts problem. Do them again with the Minitab software. You don't have to purchase it. It's available on VLabs, and you can also, if you want, you can download a 30-day copy to kind of try to play with it if you want to get good at it. It has the advantage of being resident on your laptop as opposed to try to communicate with it through MS Word. Okay, so let me try first to kind of just review conceptually what we're trying to do in reviewing the last week or so. Because of the way that the data was presented, I think that a lot of students had a lot of issues with understanding the different concepts. So I'll start again, and I'm reviewing here. I start again by looking at the different types of control charts. This is slides from presentation of week 5, last week's presentation. So there are attribute control charts, and there are defect or defective control charts. So in variable control charts, what we have is a measurement. The operator does do a measurement, and then the measurement is compared to a pre-recorded or predetermined control charts, control limits. So if the measurement is inside the control limits, everything is fine, and the operator might do this at the beginning of the shift or every 2 hours on the shift, depending on the system. Obviously, if you have a good quality system in place, you do it once a day or once a shift. If you have systematic problems, then you might do it more frequently, like I said, every 2 hours. So the idea is very, very straightforward and simple. Instead of inspecting every part for every spec, you select certain specs and you determine control limits for those specs, and then the operator measures the part and measures a sample of the part. So let's say 4 parts, takes the average of the sample and then puts the average of the sample on the variable control chart. So the variable control charts could be an X bar R, where X bar measures the average of the sample, an R chart where we measure the range of the sample. So the average of the sample points to the average of the population. They are equal. And the range of the sample points to the variability of the population. And the two are separate. So you could be in control in average, not control in the range. Using control limits are not necessarily when you do not meet the control limits. It does not mean that you are producing reject parts. What it's telling you, what it's indicating, is that there is a situation where it has to be investigated, because the control limits are set based on history. And if all of a sudden the sample average or the sample range exceeds the control chart, then that is considered a warning that something went wrong. So for instance, I use the example of a car door. If a car door and you're measuring some measurements, or a bolt, you're measuring that, and all of a sudden the bolt length is longer or greater than the control limit, whether it's lower than the lower control limit or higher than the upper control limit, that might indicate a problem. So rather than ignoring that, the idea is to stop the production line, call the quality or manufacturing engineer to fix the problem, and then make sure that the production is continuing to perform to expectations. So the problems could be bad raw materials, could be bad machining of the bowls, could be machines that are not properly maintained, not properly inspected, could be that the tools are dull and need to be sharpened. So all of these things could happen and could make the control charts or the manufacturing process go out of control. Now, we also have the moving range, and I'll highlight it here, the moving range. And the moving range is for situations where we don't make a lot of production units. So for instance, could be in the aerospace industry, where the production is in the thousands per year as opposed to the millions per year. So obviously we use different techniques for that, and then that's the control chart, variable control chart. For the attribute, we have two types. So in the attributes, we are not making a measurement. We're not asking the operators to make a measurement. We might have an automatic or a simple go, no-go gauge that will measure the length of the bolt and will tell you whether it's too short or too long according to the control limits. So the indicator of a problem here, what we're doing with these charts is we counting the probability of a unit in manufacturing is out of control. How do we do that? We do it by the number of defective units, the number of rejected units. When I say defective, it's the same as saying rejected. That means when we make a measurement, the measurement tells us, you might put it in a machine, and the machine gives you a green or a red light. So we count in a sample, and the sample usually is much bigger than the sample for the variable. The sample for the variable might be 4 or 9, something like that. But the sample for defect or defective, since it's a percentage or a probability, it has to be a much larger. So usually a minimum of 100. So if you have one defect per 100, that's a pretty, according to Six Sigma, that's a pretty bad quality. So as quality improves and we get near Six Sigma quality, then the size of the sample increases, and really using P charts or NP charts becomes impractical because it really operates within a reasonable number of samples. So for instance, if your reject rate is 2% historically, so your sample size will have to be 100. So this way, if your reject rate is 1 in 10,000, if you're going to have a sample of 10,000, that's impractical. Might as well just go to 100% inspection. The whole purpose of control charts is to reduce the amount of inspection. And if the quality is that good, then you do not need sampling inspection. You do not need P or NP charts. C charts are different. I'm not going to talk about U charts because they're kind of confusing. C charts are in a constant sample. So P charts and NP charts follow the binomial distribution, where the probability is the unit, P is the unit that you plot as the center line of the P chart or the NP chart. And P times 1 minus P, or P times Q, sometimes it's called, P times 1 minus P is the standard deviation. So when you put control limits, which are 3 times the standard deviations, then that gives you control limits. And you have to remember, P is going to be pretty small. While C charts helps us because it uses the Poisson distribution. So the Poisson distribution is similar to the probability distribution, the binomial probability distribution, except that it is a distribution where n goes to infinity. So instead of having P, Q, and N, or P and N, we only have one number, which we call lambda or C bar. And that is the average defects in a unit of time or a unit of geometry. Best example is you have a paint line and you're painting car doors. So if you have a blemishes on the car door, which is what a reject, and they're usually going to be industry standard to define what a blemish is, how big it is, how discolored it is. That's very well defined. My expertise is electronic soldering. So a solder joint has a particular shape, and that the size of that shape, it's usually round or concave, and the size of that shape determines whether that solder joint is a defect or not. If it's too much solder or insufficient solder, then these are units of defective. These are very well defined in standards of the industry. So, the fact that you have a blemish on a car door or a bad solder joint might be many different specifications or problems with different specifications that you do not know. So, for instance, in a car door, it might be the way you mix the paint, or the pressure in the paint gun, or it might be the temperature of the oven where you're drying the paint. So or the surface finish preparation, or the subcoat behind the final coat. So there might be different problems. So if you have allowed for a certain amount of blemish in a car door, or a certain amount of blemishes in 100 car doors, and all of a sudden that number is much higher, that's an indication for problem. It doesn't tell you what the problem is. It tells you there's a problem and you have to go and investigate. So it is number of defects as opposed to actual measurement. I was involved in a pretty interesting case in a factory that made contact lenses. You know, what's a blemish on a contact lens? What's a concave on a contact lens? So there's a lot of issues in terms of these control charts. And also in terms of translating the control chart information to reject rate information is another thing that we want to do in week 6. So one of the biggest problems that they asked me to consult on, okay, they had many different on the contact lens. It could be the blemishes, it could be the concaveness. So how do you add them all up? That's another problem. How do you add different, because there's maybe in a typical product there may be 20 specs. So you have a control chart on each spec? Probably not. You have control charts on critical specs. So the question is, how do you relate that to reject rate for the population, which reject rate translates eventually for the population to process capability and Six Sigma CPK. So how does that work? So that's really the purpose of week 6, and that's the purpose why I'm trying to relate that to you. The other thing is that another graph we had, which I want to review one more time for you, to kind of look at sampling versus population. So you could see the control charts right here as I'm pointing my arrow. Let's make that a little bit bigger. A little bit bigger. Here we go. So you have the control charts, and you have upper control limit and lower control limits. And there is the formulas for them. Control chart limits are X double bar, which is the center line, the average of sample averages, X double bar, plus or minus 3S. S being the standard deviation of the sample. Now remember, control charts are charts of sample averages. Okay, they're not individual points. Each point is a sample average, so it's a distribution of sample averages, and the control limits sit at 6 sigma. So if a point falls outside the control limit, either below or above, if you go back to the Z chart, as we talked about it before, when a point falls, I thought I had it, just a sec. Okay, I don't see. Oh yeah, I know what's going on. Excuse me. It is in there. So if you look at the Z chart and you look at 3, right? 3 is the 3 sigma point, and the 3 sigma point, if you have a point outside of the 3 sigma point, its probability 0.0135 or 0.135%. If you do it on both sides, then it is 0.27%. That translates to 2,700 parts per million. So that says if you have a point, and that point is outside of the control limit, the probability of that either being up above the upper control limit or below the control limit is 2,700. That's pretty low. So if you actually do get a point, that indicates, that point being outside of the control limits indicates something have gone wrong. We want to make sure absolutely that now it might be like what they call a false positive, meaning that's the way it's a black swan. That's the nature of things, and once in a while you're going to get a point outside the control limit based on the standard normal curve. But if it happens this time, then that means that something is wrong and we better investigate it. It doesn't mean if a point happens here, just for that, if a point happens here between upper control limit and upper spec limit, it's outside of control, but it is a good unit. So you got to be very careful that the upper spec limit is in no way related to the control limit. It's only related by the Six Sigma formula. So I just want to kind of remind you of that. So essentially the connection between control limits and spec limit is this equation right here. This equation says, because we assume samples are going to be less than 20, that sigma, which corresponds to the population, is square root of n, square root of sample size, times S. So S comes from control chart. It's a sample of sample averages, and then sigma comes from the population. Once we know sigma, and once we know the X double bar, the center point of the control chart, we can work them against the spec limits and we can get the reject rate. Okay, so going back to the previous chart, we get the reject rate, then the reject rate is expressed as a reject, and then it could be plotted as a reject based on history. So the three are interconnected, and I want to make sure you understand that interconnection, because that's what I'm going to ask about in the midterm, which is coming up next week. We have one more homework to discuss, and I'll try to give you as much hints as possible in the chat, the regular course chat, during the time of the course. Okay, one last thing to talk about is, again, to reemphasize, control chart, what I call statistical process control, SPC. Control charts do not improve quality. Control charts maintain quality. So the idea here, the sequence of things to do in a modern factory is you first got to get into what's called the TQM phase, or the DEMIAC phase. This is where you use qualitative tools to improve quality. Then you get into the SPC phase, or the control chart phase, and that you maintain quality. Just make the quality of the factory stable. Once you see that the quality of the factory is stable by not having a lot of out of control days in the factory, then you can apply the DOE, and the DOE is the one that's going to hopefully get your rejects really, really down into the Six Sigma level, which is 3.4 parts per million. And the idea behind that is DOE can move the average, or it can reduce variability. I mean, this is really what we try to do in the idea of showing you what a control chart is. As I said, let me go back to a smaller screen. So it plots the X bar, which is the process average. It plots the range. And the idea is it keeps things under control. While what DOE does, it can move the average. it can reduce the variability, and we measure that by the quality loss function that we studied the second week. So that's trying to wrap up the quality pieces that we've discussed so far. And it's worth spending a few minutes on it to make sure everybody kind of steps back from worrying about the numbers and the formulas and what are we trying to do with this system. So control charts maintain quality. If you have a new product, you might want to start with DOE rather than this is for an existing product. For a new product, you might want to start with DOE as to the best manufacturing processes to use, and then maintain that with SPC. This is for an existing product where it was poor quality and we're trying to convert it to good quality. And notice it did take 2 years to do that. So to put these tools in perspective and to tell you that the most important thing is control charts are distribution of sample averages. Even if the population is not normal, the distribution of sample averages is normal. Okay, and that and control charts and reject rates, the connection is process capability, CP and CPK. So these are the 3 pieces we want to connect together. Okay, so that's the high level. I wanted to pull you away from worrying about all the numbers and what they mean to focus you on these are the tools we would use to create world-class quality in a factory. And it takes a lot of work. It's not that easy. So I just wanted to make sure that you're on top of that. So I'm going to close that and go to our week 6. Now, actually, for week 6, we are not going to really use a lot of this information because I thought if I throw so much information at you, it's going to be confusing. But I need to discuss it so you could see another aspect of the quality systems is the best way I can describe it. So although this is not in the homework, this topic, and it's not in the midterm, I don't want you to just close your eyes and say, well, it's not the midterm. I'm not gonna worry about it. It's not the homework. I'm not gonna worry about it. So I'm just trying this out and making sure you just give you one more piece of the puzzle in terms of quality. So one way to look at quality is to quantify the rejects, and we quantify the rejects using the standard normal curve, and we went through several weeks to understand that. The other way of looking at it is looking at it in terms of what's called first time yields. Excuse me. So just to define it, defects per unit, okay, and first time yield. Why do we need that? If you're a design engineer and you're designing your new product, and one of the responsibilities you have as a design engineer, or at least in the design team, that you're going to manufacture this product somewhere, hopefully in your manufacturing facility nearby, and you're going to have to determine the size of the test equipment. How many test equipment pieces do we need? And of course, you need the test equipment to do 100% testing. But if there is defects, we need to, or defective units, we need to repair those defective units. And therefore, we need an area for repair and replace components in your product. So the idea here is first we agree what the defects per unit we're going to produce, and that comes out of CP/CPK. So for instance, we negotiate with manufacturing and we figure out how many defects per unit we're going to get, and we also can determine from that the first time yield. So DPU is determined by the 6 Sigma procedures that we've studied, and first time yield is just a percentage. So that helps you as you have a target of selling so many units that you're going to have X number of units that are defective. So you need so many test equipment and so many repair stations. And that's very important as part of the new product introduction. Not every product is going to come out is going to be perfect. So they're going to be defects and they're going to need to be repaired. And that's part of the design team responsibility, is to work with manufacturing to set up the manufacturing for the new product. So that again is very similar to the Z distribution. The Z distribution is kind of a standard normal distribution, but we can also approximate it with a in terms of defects and first time yield. We can approximate it using a exponential distribution. So first time yield, the reason we say first time yield, this is we put the product together and we test it. And when we test it, we're testing it, meaning we might have tested it in process, meaning while we're being assembled, we're testing it. But this is the final test, the first time we do the final test, and how many units will fail. So that's called e to the minus summation of DPU. Very little equations that kind of gets, I want to put you, wrap your head around this idea of quality planning. Okay, so first time yield is first time yield prior to test, repair, or inspection. So the idea here is we assemble the product, we're going to test it, and the first time yield is e to the minus summation of DPU. Okay? It's based on the exponential distribution. As you remember, the exponential distribution expression is a series, and it's a numerical series which goes on to infinity. The last term being very small, and maybe you use the first few terms. For our purposes, where DPU is very small, the minute you get to x squared, that number is going to be extremely small. So we just use the first term. Okay, when we have defects rate, in the 1 part per thousand, x squared is going to be a pretty small number. So the approximation of 2 to the minus x is 1 minus x, and then you can calculate the defects based on that. So the way why this is important is we can assign a DPU for each station or each assembly operation. So for instance, when we do Six Sigma, we're doing it on individual parts. But if we have a line, there's many operations. And the next slide will a couple slides from now will explore that. So now what we do is each step has a defect rate. So there's a kind of a Six Sigma calculations on each step. And therefore, there's a DPU at each step of manufacturing. And there's a reject rate for each step or yield. And then all you're going to have to do is very easy to add up the defect rates to get the total yield. So the yield is a multiplication of individual defects. Okay, so you can either do it by yield, which is e to the minus the summation of the DPUs, or just add up the DPUs. That would be another way of doing it. Here's an example. Remember, this came out of Motorola, and Motorola was really making integrated circuits or chips. So, and these chips got to be bigger and bigger. So you'd have a plate around the chip, which has all the connection, and then the operation that connects the terminal pin to the chip. The chip sits inside, and it's connected by wires, which are wire bonded. These are gold wires, wire bonded from the chip to the frame of the IC. Now they have something called, they have chips which are where, because the number of pins gets to be so big, they have called ball grid array. And what they do is rather than have pins, they have little solder balls at the back. And essentially the whole back is covered with pins. So you can have, this one is 256 connections, but they got into as much as double that and triple that. and they go by double. So they've gone as much as 1,000 connections or 500 connections, and then of bumps, solder bumps underneath the chips to reduce the amount of real estate, so you can cram the electronics in the iPhone and things like that. So there's 256 connections per IC frame and 2 wire bonds per connection. So wire bonding was a very important operation in the IC manufacturing process. So if the DPU is 1 in 1,000, I'm sorry, 1 in 10,000, which is 100 ppm, what is the first time yield of this operation? Okay, so if the yield per single operation is 100 ppm or 1 in 10,000 for wire bonding, what is the first time yield? So the first time yield is, according to our formula, is E. There's 512 opportunities for a problem. I mean, actually, when we say there's 512 connections, there's 2 wire bonds for the wire. There's 512 wires and 2 wire bonds. It's really should be times 2, but I'm trying to make it simple. So E to the minus 512 times 10 to the 1 in 10,000. So E to the minus 512, which says 95%. So that's one way of doing it. You can run your calculator and see that's the number you get. Or you could say the probability of each one, okay, is 1 minus the DPU, is the probability of each one using this approximation of 1 minus DPU, and there's 512 times that. So essentially, it's 512 over 10,000 minus 100, which is the 1 out of 10,000. Oh, 51,200 connections at 1 in 10,000 DPUs. That's 512 defects per 100 IC. So essentially, you can do it one of 3 ways. Either do it using the first time yield, E to the minus number, or use the approximation, or use the total. We'll use the total defects, total opportunities for defects, and you get the same number, which is 500. One way of visualizing, and I'm not going to ask you on this in class, I'm just giving you the concept how these things work. So one way of looking at it, if you have several operations, and then out of the several operations, you get the first time yield. So the question becomes, should I just assemble the product and then test it at the end, or it's going to be the acceptance rate of the product or the first time yield is very low, and therefore I need to test in process. So that's the decision you have to make as a part of the design team. And what is the line capability? So the idea here is a process system of 50, 99, 95% capable, meaning each station, each in-process station is 99% capable, produces 1% defect. If you have 50 of those, give you an idea, in my expertise, if you make a printed circuit board, there's 30 operation. If you make an integrated circuit, there's 200 operations. So 50 is not a big number in the IC world, okay? So the first time yield will reduce this 99% for each station to 60% for the whole line, okay? So that's what I'm trying to say in the sense that if the individual manufacturing station quality is not at the highest level, what you're going to produce is just essentially garbage. So that's why this Six Sigma was needed, especially in the IC industry, is because the opportunity for defects are so vast that you really had to have Six Sigma quality, so that when you add up, you have to remember in the ICs, they have these flat 12-inch discs, which are full of thousands of ICs. These are the chips that are inside. They cut up, and then they are either placed with wire bonding or placed on solder bumps. and made into an integrated circuit, you really need Six Sigma quality in order for that disk of ICs that is being passed through the lines, through 200 lines of operations, 200 stations in the line. You need Six Sigma quality in order to have a reasonable 90% acceptance for each IC. And the way they do it, they test it automatically, and then they would throw a spot of ink on the IC that doesn't work, so that when you cut it up, you'll throw that IC over. Here's an example, and I was consulting several companies on that, and saying this way: if your product can, that's another example of demonstrating this idea of what quality you need in your product design, so that the production line that makes your product will be reasonably in high quality. So if your product contains 10 printed circuit boards, and you set a goal of 95% auto test yield for your product, okay? What is the yield of your product? Once you put everything together, what's the yield of your product? If you have 10 boards, 10 printed circuit boards, and each one of them, and your goal is 90, and each board has 95% auto test yield, meaning each board has 5% defects, what's the product turn on yield, first time yield? If the DPU is 0.5, which is 5% of each board, each of the 10 boards will be defective. E to the minus 10 times 0.5, you do the math, and it's 60%. So while individual boards are 95%, when you put them together in a product, they are 60%. So that's pretty lousy. You have to hire a lot of technicians to repair and replace the product or the boards. So what you want to do is you might want to improve the quality of each board by a factor of 10. So instead of 95, you go 99.5, which would be 0.5%, 0.5%, instead of 5 out of 100, 5 out of 1,000, right, which is DPU of 0.05, then you would get a turn-on yield of 90%. So you really have to increase your individual quality on each station, each manufacturing station, to get a turn-on yield for the line that's reasonable, and you're not hiring tons of people for testing and repair. Before the Six Sigma revolution, test and repair was a third of the manufacturing cost for products. And that's why when the Japanese competition came in the late, about 20 years ago for electronics, American companies just could not compete because their production cost was high. Their production cost was high because 30% of their production cost was quality defects. So if you have 30% of your cost in quality defect and your competitor has a much lower number, there is no way you can compete financially in this product. And that's what's important about that. I did another example for another company in terms of assembly of printed circuit boards, and made it very simple. There's 3 operations in the line. There's soldering, there's assembly, and there's the parts. These are sources of quality. And I went through the operation, and I said, as your technology increases and you have more parts in your product, your first time yield increase. I don't want to go through the math because you can do it itself, but the example I gave him is this. If your product has 100 parts using your quality, and these are the quality numbers for your part. If your product contains 100 parts, your first time yield is 90%. If your product, as you have more advanced technology, you need more parts. If your product increases by 10, you don't do anything about quality, you have the same quality as shown in the top, your yield drops from 90 to 35%. So if you have a next generation product, and the next generation product is going to need a lot more parts in your current generation product, then that is a big problem. Okay, this is the end of my week 6. Now, a lot of what I talked about will not be in the homework. I will discuss the homework in the live chat that we have for the course. And I just wanted to give you one more view because I'm giving you just the basics on uh, Six Sigma and control charts for one station, one part. But when we put them together in a line, how do we do the math? We're going to discuss that more in the second half of the course. But I wanted to answer that question. How does that work for one workstation and one assembly station in the production line versus the whole line? So I have another week to concentrate on that. What I want to spend the next, I've gone now about 45 minutes. So I want to spend about 20 minutes reviewing the course so far, and then the topics I'm going to cover in the midterm. So let me close this one, and we'll talk now about the midterm review slides. So I'm going to have 8 questions midterm. The first 7 have to do with the topics we discussed, and the 8th question is kind of yes and no. Excuse me. Bunch of questions. So one of the questions I'll ask is structured analysis, process mapping. This is the first week of the course. So I'm going to describe a process, a situation, and I'm going to ask you to do context diagram and also do the data flow diagram. What I'm looking for is this, which is what we talked about. We're looking for a source or destination, which is a triangle, a process, which is a circle, and the context diagram contains one title process, does not have in it a data store, then one data flow diagram level 0. So we have data flow diagrams, which is the arrows, and data stores begin to show up, and then data store repeated so that it looks like a neat data store graph. We have a double line. So there's an example of a consulting job that I did to try to help a production shop coordinate between different shifts. Which shift takes which job, and there was no control over which shift takes it. So the second shift was taking the easy jobs and leaving the tough jobs for the shift, leading to problems in the factory floor. So we created a system. I'm not necessarily interested in explaining the system to you, but just telling you what I'm looking for. As I said before, we look at the source and destination, and they are the context diagram, and they are rectangle. We look for the process that we're trying to do a process map for, and that's production planning board, which is we decided we're going to create a planning board to communicate between the different shifts, and then the names of the data flow diagrams. So when I go and look at the data flow diagram, I want to see all 3 pieces here, except that the main process, the production planning board, is going to be broken up into more than one process. So all the data flow diagrams in the context diagram, data flow arrows, have to show up in the data flow diagram. So yielded product plan, production plan, and results daily production plan, the results and daily production plan gotta show up in the data flow diagram. I also need to see them data stores. Okay, so I am not quibbling about how you're going to do it, because there's no one way to do process mapping, but I want you to follow the procedures in terms of keeping track and keeping connection between the context diagram and data flow diagram level 0. I don't want to go further than that, and I only want you to do one. I'm going to give you 5 choices depending on your last digit UML ID, and I only want you to do one. So I want to make sure you are following up on that. So one of the 7 questions, the 8th question will be yes or no. One of the 7 questions will be on process mapping. Another one will be on GR and R. So this is the example I gave in the slides. And again, we want to look at what we're trying to do. We have 5 parts and 2 operators. 5 parts, 2 operators. So each operator tests the 5 parts twice. So operator A tests the 5 parts once, tests the 5 parts twice. So we have an operator A average, and we have an operator A R bar. Operator B does the same. Looks at the same 5 parts and test all 5 parts once and test all 5 parts again. So each operator has a range for each part and an average for all 5 parts. So each operator has an X bar, which is the average of the 10 measurements they made. I mean, you can see we added up the average for first time and the average for the second time, and then excuse me, and then we averaged, and then we add them up in this particular case for the X bar. And then we have an R bar for each operator. We have an X bar for the second operator and a bar for the second operator. And then we have a summary for both operators. We have an R double bar and an X diff. R double bar is the average of R bar operator 1 and R bar of operator 2. R double bar, that is it, the average of the 2 R bar, and the X diff is the difference of the averages of the 2 operators. Okay, so R double bar points to sigma of the equipment, and X diff points to the sigma of the machines, of the operators themselves. Okay, so R double bar is the sigma of the equipment or the machine, and X diff is the sigma of the operators. So sigma of the equipment is R double bar over D2. We have a table for D2, so that's not a problem. I'll give you that table. And then when we get the equipment variation, so that's the sigma. The equipment is 515. That's the old standard. Or we can say 6 sigma of the operator. If you use Minitab, they're going to want 6 sigma. If you use many of the other individual GRR, they want 515. So you got to be very careful to tell me which one you're going to use. So that's for the sigma equipment variation for the equipment. For the operators, which is called appraiser variation. Okay, so what we have is of course we have one more number for the equipment variation, which is divided by the tolerance of the equipment. Okay, so it's the tolerance, so V over the equipment tolerance percentage wise. And then sigma appraiser variation, we take the X diff over D2 star squared. So X diff divided by D2 gives us the equipment the appraiser variation. We square it, and what we have to do is we have to subtract the equipment variation from it. So that is the formula. You got to be very careful. So what is N and what is R? N is 5 parts. There's the 5 parts. And R is how many times repeated. We have 2 operators. So N times R is N is 5 and R is 2, so that's 10. So you take the sigma squared of the equipment, divide them by 10, and you get appraiser variation, sigma appraiser variation, multiplied by 515. If you're using traditional GR&R, multiply by 6 sigma if you use Minitab, and you get appraiser variation. And then GR&R is the what they call RMS, or root mean square of the two, and you get percent GR&R. I'll ask in the midterm, I'll ask more about part variation as well. Make sure you look at the homework that I mailed you, the solution that I mailed you, to see how we do that. So what we do for the part variation is we look at the average, each part here. So what do we have? We have 5 parts measure 4 times. Operator A measures 2 times, and operator B measures 4 times. So 5 times 4, we have 20 measurements. 5 parts, each part measured 4 times. So what we do is we create another column here at the end, which is average of each part as they've been measured 4 times. So you have another column called part averages, which is all 5 parts with 5 averages. And then we take the x diff of that, and the x diff of that gives us the sigma of the part. So the sigma of GR&R and the sigma of the part gives you the sigma of the total. And then you can do the variation here and see what percentage of spec is up by variation of the R. Is we want less than 10%. That the measurement equipment error as measured by equipment variation, operator variation, and part variation is less than 10% of the spec. You're not eating more than 10%. I mean, you can tolerate up to 30%, but beyond 30%, your measurement error is most of your spec. And that's tough. And the way you handle that, and the way that's handled in industry, is you take that spec and you reduce it by the error of the measurement, or the error, which includes the part. So if it's 30% and you have a plus or minus 10, you got to reduce your spec to plus or minus 7, because plus or minus 3 out of that 10 is eaten up by the error in your equipment. So if you ship your product to another company and they do incoming inspection on it and they have a different system, the only way to reconcile these two is to do a GR&R on both sides. And I've been involved in a lot of situations like that, and that's extremely important. Okay, so that's the GR&R problem. So I'm going to give you not a lot of parts, probably going to give you 2 or 3 parts, and so that you don't have to get involved in the math and all that. So you do that.